Automatic Addison.
In the previous tutorial, you learned how to leverage ROS2 control to move the robotic arm manually by sending raw joint commands to the robot. This exercise is great for learning, but it is not how things are done in a real-world robotics project. In this tutorial, I will show you how to set up a ROS2 software called MoveIt2 to send those commands. MoveIt2 is a powerful and flexible motion planning framework for robotic manipulators. Using MoveIt2, instead of sending manual commands through a terminal window, allows for more sophisticated, efficient, and safer motion planning, taking into account obstacles, joint limits, and other constraints automatically. By the end of this tutorial, you will be able to create this. Before we dive into the tutorial, let me explain how MoveIt2 works with ROS2 control by walking through a common real-world use case. Suppose you have a mobile manipulator, which consists of a wheeled robot base with a robotic arm attached to it. You want to develop an application that performs a pick-and-place task. Your cool application starts by telling MoveIt2, pick up the object at location A and place it at location B. MoveIt2, with help from Nav2, the navigation software stack for ROS2, plans out the detailed movements needed, reaching for the object, grasping it, lifting it, moving to the new location, and placing it down. These plans are sent to ROS2 Control's Controller Management System, which has specific controllers for the arm, gripper, and base. The arm controller, joint trajectory controller, for example, breaks down the plan into specific joint movements and sends these to the resource management system. The resource management system communicates these commands through hardware interfaces to the actual robot parts, or their simulated versions. As the robot executes the pick-and-place task, sensors in its joints and grippers send back information about the position, force, and status. This feedback flows back up through the system, allowing our application and MoveIt2 to monitor progress and make adjustments if needed. This setup allows you to focus on defining high-level tasks while MoveIt2 and ROS2 Control handle the complex details of robot control and movement coordination. Now let's look at another diagram which shows the specific controller and topic names. This gives us a more detailed view of how MoveIt2, ROS2 Control, and the robot components interact. Your cool application initiates the process, defining tasks like pick-and-place operations. MoveIt2 contains a path planning component that generates trajectory commands. These commands are sent to the joint trajectory controller, which manages the arm's movements. For mobile robots, Nav2 can send twist commands to the diff drive controller, controlling the base's motion. The system includes several specialized controllers. The first one is the joint trajectory controller for arm movements. Next one is the forward velocity controller for speed control. This is optional, only needed if you need direct velocity control for high-speed operations. Then you've got the gripper controller for end effector actions, allowing you to open and close the gripper. Then you got the diff drive controller for mobile base navigation. These controllers communicate with hardware interfaces for the arm, gripper, mobile base, and the Gazebo simulation. As the robot operates, sensor data flows back through these hardware interfaces. This information includes position, velocity, force, and status updates. The joint state broadcaster and force torque state broadcaster collect this feedback data. This state information, the joint angles, is then forwarded to RViz for visualization and to MoveIt2 for real-time monitoring and adjustment. Now that you understand how all the pieces work together on a high level, let's start setting up our robot with MoveIt2. We're going to begin by creating a new package. So let's go to CD, source, CD mycobot ROS2, CD mycobot MoveIt2, MoveIt config. Let's clear. All right. And let's just take a look at package.xml in here. And we need to flesh this document out. So we already created the actual folder for mycobot MoveIt config earlier in an earlier tutorial, but let's flesh this package.xml out right now so that we get the appropriate packages. And I want you now, under that BSD3 clause in immense CMake, And then the build tool, which you can see right here. I want you to go below here and add these blocks. Add this whole block right here, these dependencies. So we've got the MoveIt ROS planning interface, the MoveIt ROS move group, MoveIt Kinematics, MoveIt Planner's OMPL, MoveIt ROS visualization, RViz tool, and RViz visual tools. And below that, we need to add some more dependencies, execution dependencies. And let's do that down here. So down here, we've got the exec dependency. We got MoveIt Simple Controller Manager, MoveIt Configs Utils, and the Pilz Industrial Motion Planner. You don't need to know what all this is now. Just follow the steps. Let's put that down here on line 20. And once you've done that, I want you to save, close it. Let's go back up here to our workspace. Actually, I'm going to open up a new terminal so we can just do it all in here. CD // and we do ROS to workspace. And here we are. Now let's do ROS dep install -- from - paths src space -- ignore src -r and then -y. Okay, it looks like we need to install the ROS Jazzy RViz visual tools. All right, and let's just type the password so that automatically installs. This will install any missing dependencies. Okay, and when you're finished with that, you should get a message at the bottom that says all required ROS dependencies installed successfully. All required ROS deps installed successfully. Clear this out. Now, folks, I've got a nice handy alias, which you've seen in previous tutorials, called build. I like to have this alias because I really just get tired of CDing, changing directories to the workspace, running colcon build, and sourcing the bash rc file. And remember, for you folks who don't remember, get it tilde.bash rc. In the bash rc, I do all these commands like sourcing the ROS2 Jazzy distribution and sourcing the workspace. I put all this stuff in the bash rc so that anytime you open a new terminal window, the environment automatically is set up. Okay, so here we got clear. Let's type the build command. This runs colcon build and then sources the bash rc. All right, everything built. And let's clear. So remember, by convention, I just want to show you one thing here before we move forward. I'm going to go to my MyCobot ROS2 package. You've got the MyCobot MoveIt config. So this is by convention in a real robotics project. This is the naming convention. Okay, you typically would put the name of your robot, then an underscore, and then MoveIt_config. So make sure you do that for any robot. So let's say our robot is Addison bot. So I would do Addison bot underscore MoveIt underscore config. So Addison bot underscore MoveIt underscore config. Whatever your name is, it's robot name underscore MoveIt underscore config. And that's how MoveIt knows that this is a MoveIt based package. So now we're going to clear that out. Let's create configuration files that will enable us to tailor our robot for MoveIt 2. We'll do this process manually, which is recommended, but you are welcome to use the MoveIt Setup Assistant. And I'll show you that right now. Let's open up Firefox, go to Google, and I'm going to type in here the MoveIt Setup Assistant. Okay, and here are all the instructions for the MoveIt Setup Assistant. You can walk through all those steps. I like to do it manually, so I have more control over where the files are, what's going where, and how I set up everything up. And that's what we are going to do now. So to start, MoveIt 2 requires configuration files to go into the config folder of the package. So you're in your MyCobot ROS2 folder right here. let's go inside the MoveIt package. We're inside here now. And let's see what we got in here. Okay, we already have it. So we've got a config folder. Good. Okay, and then one layer below that in config, we've got the name of the robot. So CD, let's do CD MyCobot 280. Okay, and we're in here. So the first thing we need to do is to set up the SRDF file. And let's do that now. Okay, so we have this folder. All right, I'm going to go to the downloaded MyCobot ROS 2, MyCobot MoveIt config, and config, and then in here. And this is what I pulled off of GitHub. Obviously, you can pull all this from GitHub and just do it, but I want to show you how to set things up bit by bit, piece by piece, so that when you are in a real world environment, when you're setting up a real world robotic arm, let's say your own robotic arm, you know how to build this up from scratch. That's where the learning is at its strongest. So I want to get this guy, this MyCobot SRDF. So let's start. I'm in here. Let's just do a touch MyCobot _280.srdf. And let's do a get it MyCobot. Let's open it up. It's blank right now. I'm going to go over here to what I already have from GitHub. Let's do a copy and then a paste and save. And let me just talk a little bit about what this is. So this is an SRDF file, okay? What is that? Okay, SRDF stands for Semantic Robot Description Format. It's a file that tells MoveIt how your robot prefers to move and interact with its environment. It is a supplement to the URDF file you got experience with in an earlier tutorial. The SRDF adds semantic, meaning meaning-based information to the robot's description that isn't included in the URDF, the Unified Robot Description Format. This file includes things like naming groups of joints or links, for example, arm, you can see right here, or gripper, which you can see right here. We also define default robot poses. So we've got the home pose right there. We've got the ready pose right there. All right, and then for the grippers, we've got open and closed and half closed and all that. Default robot poses, both for the arm and then also for the gripper. And we also, inside this SRDF, we define which parts of the robot should be checked for colliding with each other during movement. And that's down here. We need to do this step because checking every possible collision between all parts of the robot for planned movement can be time-consuming, especially for complex robots. So you've added it, you save it, all right, and now close. Okay. Now we are going to close out here and we are going to create a configuration file for the initial positions of the joints of the robot. Okay, we're going to do touch initial _ positions .yaml. Let's do a get it. Go over here. Go into our downloads, MyCobot ROS 2, MyCobot MoveIt config, inside here. So here's the path. So downloads, MyCobot ROS 2, MyCobot MoveIt config, and MyCobot 280. Again, all this is on the GitHub, but we're doing this step by step, bit by bit, click by click, keystroke by keystroke. Let's open this up right here. I'm going to Control A on that, Control C. Let's go back and Control V to paste and save. So here we have the default initial position for each movable joint of the robotic arm. Okay, save the file. So just to make clear, this initial _ positions.yaml in MoveIt, it specifies the starting joint positions for motion planning. It overrides any default position set in the URDF file. It allows you to set a specific initial configuration for your robot in MoveIt without modifying the URDF, providing flexibility in defining the starting point for motion planning tasks. So let's save it and close. We've got some more configuration files coming. You can see all these. Let's just go piece by piece. Okay, now let's add another one, the joint limits. So touch joint underscore limits dot YAML. File names are important, folks. MoveIt likes a specific file name for these different components. So we open it up, blank file. Let's go over here. Let's go open this one that we have from our GitHub. And we're going to select all. We're going to copy it all. And go over here and paste. Save. Okay, so what does this file do? The joint underscore limits.yaml. This code sets the velocity and acceleration limits for each joint in our robotic arm, which is used by MoveIt 2 to control the robot's movements. Even though we have joint limits for velocity already defined in the Chakra file, the URDF, this YAML file allows for overriding. Defining joint limits specific to MoveIt 2 is useful if you want to impose stricter or different limits for particular applications without modifying the URDF. It provides flexibility in adjusting the robot's behavior for different tasks. Save it and close. Close that and close that and close that. Let's just clear things up here. Okay, now let's add Kinematics.yaml. So we're going to do touch Kinematics.yaml. Get it? Kinematics.yaml. Let's go over here. Remember, guys, slow is smooth, smooth is fast. No need to rush through all of this. Take your time. Minimize mistakes, and you'll do it faster in the long run. So let's open this up, Kinematics.yaml. Control A, Control C. Let's go over to get it. Let's Control V that. All right, we've got our Kinematics.yaml in there. Let's close this stuff out. Let's just keep that in front of us. So what does this file do? Kinematics.yaml. It configures how MoveIt 2 calculates possible positions and movements of the robot's arm to reach a desired point in space. It specifies the mathematical methods, precision, and time limits for these calculations, which MoveIt 2 uses to plan the robot's movements. Save the file and close. Now let's add the MoveIt controllers. I'm going to do touch and then MoveIt underscore controllers.yaml. All right, let's open it up. Let's go over here. MoveIt controllers. Open this puppy up. Control A, Control C. Let's go over to get it. Control V. Save. Let's close this out. Close this out. Okay, MoveIt controllers. This YAML file tells MoveIt 2 how to convert its motion plans into instructions that the ROS2 controllers can understand and execute on the real or simulated robot. Without this file, MoveIt 2 wouldn't know how to make the robot actually move using the ROS2 control system. So MoveIt 2 sends desired joint positions or trajectories to the ROS2 controllers, which then manage the low-level control of the robot's motors. This integration allows MoveIt 2 to focus on high-level motion planning while relying on ROS2 control for the actual execution on the robot hardware. And we can see in here that we have two ROS2 controllers available. We've got the arm controller. This is a joint trajectory controller, okay, for the robot arm, right here. And we've got the gripper action controller right here. Okay. So we can see a list of joints associated with each controller here and also here. The arm controller uses the follow joint trajectory tongue twister, follow joint trajectory, action interface. We can see that right here and here. The follow joint trajectory action interface is a standardized interface in ROS for controlling the joint positions of a robot over time. It allows MoveIt 2 to send a trajectory, which is a sequence of joint positions and their corresponding time stamps, to the robot's joint controllers. Okay, so follow me here. Here's how it works. So MoveIt 2 plans a movement which results in a series of joint positions over time. Okay, move the arm here. MoveIt 2 plans the movement. It then sends a series of joint positions over time. This plan is then packaged into a trajectory. Think of it as a list of goal positions and radians for each joint of the robotic arm. MoveIt 2 then sends this trajectory to the appropriate ROS 2 controller using the follow joint trajectory action interface. This interface is like a protocol MoveIt 2 uses to communicate with the controllers. And then ROS 2 controller system receives this trajectory, processes it, and relays it to the hardware interface. And then the hardware interface sends the commands to the microcontroller, for example, the Arduino, to move the robot's joints accordingly. So that's how it works. Follow joint trajectory. We got our gripper command action interface. So let's save it and close. Okay, now let's add the Cartesian speed and acceleration limits. So I'm going to clear this. And let's go to touch, Pilz underscore Cartesian underscore limits dot YAML. Let's open it up, get it, Pilz. Okay, and let's go over here, config. Open this puppy up. Okay, and let's do Control A, Control C, and then Control V. All right, there we go. That's how the file looks. So what does this file do? And why do we need to add it? Well, Pilz focuses on simple, predictable movements like straight lines, circles, and direct point-to-point paths. It works by calculating a clear, predefined route for each part of the robot to follow, ensuring smooth and safe motion from start to finish. Think of Pilz as a careful driver that always takes known reliable routes rather than trying to find creative shortcuts, making it perfect for precise tasks where you want consistent, controlled movements. So while default planners like the OMPL, let's Google that so you can see what that is here. OMPL, MoveIt. So the default planners like the MoveIt Open Motion Planning Library, this OMPL right here. You can see this website. So MoveIt.ai/documentation/planners. So this is the default planner, Open Motion Planning Library, OMPL. They work best for dynamic environments where you can have unexpected obstacles. Think of people moving around, objects left on tabletops and counters, etc. The structured and predictable nature of Pilz is advantageous in a scenario where the environment is well structured and controlled. Okay, so we have defined that. Let's close that here. So by the way, before we close real quick, I just want to say that this file sets the acceleration and the speed limits for a robot's movement in space. So what that means is it defines how fast and how quickly the robot's end effector, the gripper, can move and rotate in a Cartesian space. That's the X, the Y, and then the Z directions to ensure safe and efficient operation within the robot's workspace. So you might ask me now, okay, so why do we need this file if we already have velocity limits set in the URDF file? So I'm going to go over here so you can see what I mean here. My cobot ROS 2 description. URDF, Mac, my cobot. So you can see we've got these joint velocity values, and let's go down here. right here, this limit. So here's our URDF for a robotic arm, and you can see the velocity, joint velocity limits in radians per second right here. So why do we need this right here if we're already setting the joint limits inside the URDF? Well, the URDF and the MoveIt configuration files serve different purposes when it comes to controlling the robot's motion. The URDF contains velocity limits for each individual joint. Okay, we've got a 6-axis robotic arm, so 6 joints there. Then we've also got the gripper. And that determines how fast each joint can move, right on this line, this limit effort. So these limits are important for controlling the speed of the individual joints, for example. But on the other hand, okay, we've got this file. The Cartesian limits in the MoveIt configuration are used to control the speed and motion of the robot's gripper in 3D space. And these limits define how fast the gripper can move and rotate in the world coordinate frame, the XYZ axis. These limits are essential for planning the overall motion of the robot, ensuring that it moves safely and efficiently when performing tasks. So while the URDF velocity limits over here are important for controlling individual joints, these MoveIt Cartesian limits over here are still necessary for proper motion planning and control of the gripper's movement in 3D space. By the way, you might be wondering, what the heck does Pilz mean? Well, Pilz Cartesian limits, Pilz. Pilz refers to a company called, and let's just go here so you can see this on the screen. I'll go Google, do Pilz. Come on, Google, get out of here. Pilz. And I'm going to do GmbH Co. KG. So it's the name of a company right here. Pilz. Okay. It's the name of a company based in Germany. That's what that stands for. It's a German automation technology company that specializes in safe automation solutions, including robotics. So let's get out of here. Get out of here. Okay, let's clear. Now to make all this work, we need to add a file called Pilz Industrial Motion Planner Planning Planner.yaml. That's a mouthful. We'll do it step by step here. So let's go over to the config file. Let's do cd ... Okay. cd ... Okay, so we're inside the ROS2 source MyCobot, ROS2 MyCobot, MoveIt config. All right, and inside this, let's create it. So we're going to do touch and Pilz, P-I-L-Z, underscore industrial, underscore motion, underscore planner, underscore planning, .yaml. There, we got it right there. Okay. And let's move this inside the config folder. So we're going to do move Pilz config. Okay, so cd into the config. And here it is right here. So you've got this Pilz Industrial Motion Planner Planning.yaml inside your config folder. All right. And let's just open it up. We're going to have a blank file. Now let's go over here to our GitHub repo. MyCobot, MoveIt config, and Pilz. Let's open this with Get It. Let's copy this whole thing and let's paste over here. Okay. So what does this file do before we exit out? This file preprocesses the robot's motion planning request to make sure it meets certain safety and feasibility criteria, like ensuring the robot's starting position is safe and within allowed limits before planning its movement. So save and close. Okay, now let's add a pipeline file for another planner called the Open Motion Planning Library. I spoke about this a few minutes ago. We're going to do touch OMPL underscore planning.yaml. Let's do open it up. Now let's go over here to the repo, open this puppy up, Control A, Control C. Let's put this down over here, save it. Close, close, and clear. OMPL planning.yaml, perfect. So let's open it up. Oh, that's a lot of stuff. This is a lot of text. Don't be intimidated, folks. It is a lot of stuff. It's a lot of stuff. Let's just talk about it. What does it do? So this OMPL is a sampling-based motion planning framework integrated into MoveIt 2, okay, and it provides various probabilistic algorithms like RRT, PRM, and variance. You don't need to know what all those means, but essentially what they do is provide a collision-free path from point A to point B for your robotic arm. So OMPL handles the complex task of planning feasible trajectories while avoiding obstacles, though it doesn't inherently optimize for smoothness or dynamics. So make sure you have saved the file and you close it. Okay, now let's add a pipeline file for another planner called STOMP. STOMP. And STOMP stands for Stochastic Trajectory Optimization for Motion Planning. Let's do that now. So we do touch, STOMP underscore planning dot YAML. Okay, got it. Let's open this up. STOMP. Let's go over here. Open this puppy up. Control A, Control C. Let's add that. Control V. Got the STOMP there. Okay, let's open it up one more time. Okay, so what is this? What is STOMP? Okay, so STOMP is a method of planning robot motion that uses random adjustments to improve paths. Think of it like constantly fine-tuning a rough sketch until you get a perfect drawing, but for robot movements. So you've got this file, let's close it, and that's all we need for that. Okay, now let's clear this out. And now we're going to create a file that sets the parameters for visualizing all this in RViz. So let's go back, cd dot dot. We need to do a make dir RViz, and we want to cd into the workspace. cd RViz. Now we're inside it. And let's do touch move underscore group dot RViz. Okay, let's do get it move group dot RViz. And we're going to go over here to the downloads. MoveIt config RViz, and open this up with your favorite text editor. Control A, Control C. Let's go over to get it. Control V. You all know RViz, okay? And make sure that smooth group RViz is there. And save it and close it. Alrighty, folks. Now let's create a launch file. All right, let's go inside to here. Okay, let's go into CD launch. Okay, and I'm in my Cobot, MoveIt config package, and inside the launch folder. And let's do touch move underscore group dot launch dot py. To get it, move group dot launch dot py. Go here, downloads, the config, launch, open it up. Control C and Control V to copy and paste. And here we go. Let's open it up again. It's inadvertently closed it. Okay, this is our launch file. So what does this launch file do? Well, this launch file launches MoveIt and RViz. And you can go through it at your own convenience and take a look at the different pieces. But the main beef here is the launching of MoveIt up here in this block and RViz, starting RViz. Save it. Okay, now let's add the setup assistant file. So this setup assistant file we're going to create is typically created automatically when you use the MoveIt setup assistant to configure your robot, but we're going to create a basic one since MoveIt expects this file to be inside your package. Otherwise, if you don't have it, it will spit out warnings if it is not in the root of your package. So let's create a file named .setup_assistant in the root directory of your MoveIt configuration package. So cd ... Okay, and we're going to do touch.setup_assistant. Do getIt.setup_assistant. Open it up. Let's go over here. Okay, it's not over here. So I am going to find it on my GitHub. It is there on GitHub. All right, I'm going to copy it and paste it in here. See, that worked. Okay, it did work. So you want this block right here to be in your .setup_assistant file. Make sure your .setup_assistant is in the root of your package. So remember to update this file. So if you're using different pathways and different name for your robot, remember to update these lines from mycobot 280, mycobot 280 to whatever your robot is. And obviously you can also update the author name, author email, and so forth. So let's just save and close. Okay, let's do a dir. Okay, you can see our setup assistant right here. It's hidden. Okay, and we need to set the file permissions. So to do that, let's do sudo change mod 644.setup_assistant and enter. Password. And let's see. Okay, there we go. Let's close it. All right, now let's add an RGBD camera to our robot so that we can eventually run a pick and place task. Let's start by creating a URDF file for an RGBD camera. So an RGBD camera captures both red, green, and blue colors, okay, images, and depth information, allowing it to see the world in 3D just like your own eyes do. So Gazebo has many sensors available, including one specifically for an RGBD camera. We will add to the URDF we currently have. So let's go to cd ... mycobot ROS2 and then cd mycobot description meshes. Okay, there's our message meshes. So cd_d435 cd visual. Okay, and so this is where we are right now. So make sure that in your mycobot description meshes D435 visual, you've got this file, this D435.stl file. Make sure you got it there. Okay, now let's go to cd ... cd ... cd ... Okay, description. Let's go to URDF, sensors. Okay, sensors. And let's create, actually, you know what I'm going to do? Let's just go to it through here. I think it's going to be easier. I'm going to ROS2, source, mycobot ROS2. mycobot description, URDF, sensors. Okay, it's empty. Let's go to the downloads. Go to new window, downloads. I'm just going to copy and paste it in here. The description, URDF, sensors. And let's copy. And let's paste that in there. Okay, it's called Intel RGBD cam _ d435.urdf.chacro. And this is it. This is our camera, our RGBD camera. All right, it is in the right location. Close it. Now let's edit the main robot state publisher file with the use camera parameter. I'll show you what it should look like. Okay, let's go to cd ... cd ... cd launch, cd robot state. Let's see what we got in here. Robot state, so it's a get it robot state launch. Publisher.py. Just go through here. Let's see if we've got our use camera in here. Okay, use camera. Got it false. We got all that there. Got the use camera parameter defined. Okay, let's make sure we've got our launch configuration right there. Use camera. Okay, all that looks good. Okay, let's go, and now let's just check to see if we've got our ROS2 bridge parameter file. I'm going to clear that out. Go to cd ... cd ... cd mycobot gazebo. Cd config. And we need to make sure we've got this ROS.gzbridge.yaml. It is there. Just verify that with what we've got on GitHub. Yep, all matching up. It's looking good, looking good. Okay, now let's go to the CMakeLists.txt. And we've got config, launch, models, and world, as we should. That's looking good. Now let's edit the main launch file to bridge the 3D point cloud topic over from Gazebo to ROS. So we're going to go to, let's go into launch, see what we got in here. Get it, mycobot. Okay, everything okay over here. Let's just verify. I'm just going to walk through, look and see what I've got. The bridge. ROS image bridge. Depth image. Here's our bridge. Got an image bridge and a ROS bridge. I think that's looking pretty good. Nothing out of the ordinary. Okay, nothing commented out. I think that's fine. Okay. Just go back and double check my, let's go here. Okay, yeah, these are our point clouds, so we're launching the ROS GZ bridge properly. Okay, and let's go to clear. Now let's go to cd ROS to cd source, cd mycobot ROS2, cd mycobot MoveIt config, cd launch, in here now. All right, let's see. MoveIt config launch. No, we're in the wrong folder. Sorry, folks. Let's go to MyCobot bring up. Yeah, that's where it is. So cd MyCobot bring up. cd scripts. And let's open this gazebo.sh. Okay, let's just make sure we got it right. Single script to launch the MyCobot. We're cleaning up everything fine. Sigint sigterm, launching. Gazebo, MyCobot. Load controllers, true. World file. Use camera, true. Use RViz, true. Use robot state pub, true. Use sim true, true. True, true, true. 0, 0, I'm going to do 0.05. Okay. And then we got 0, 0, and 0. So that looks good. Save and close. MyCobot Gazebo.sh. Okay, now let's create another script. Touch MyCobot _ 280 _ gazebo _ MoveIt.sh. Get it? Let's open that. Okay, let's see if we've got that over here. We do. We do. Let's open that. Control A, Control C. Let's go over here to get it. Control V and save. So, got that file. Let's close all this stuff over here. And save. So, MyCobot _ 280 _ gazebo _ MoveIt.sh. Let's close all this. So, you now should have 2 startup scripts in here, right there. And let's just double check this one. Use cameras true. Okay, as we expected. And clear. Okay, now let's check our load ROS2 controllers launch file. I'm going to do a cd ... cd ... cd MyCobot MoveIt config. cd launch. And let's go to open up the load ROS2 controllers. And let me just make sure I've got my delay. Yeah, we've got our delayed start. Excellent. Close it. Okay, now let's edit the package.xml file with the dependencies. So I'm going to do cd ... clear. And let's open up package.xml. And let's just verify everything looks good. Got our MoveIt planning interface. Everything looks good. Let's close. Okay, let's check this CMakeLists.txt. So get it. CMakeLists.txt. And we need to add some stuff in here. So I'm going to go over here. Going to go to the downloads, MyCobot. MoveIt 2. Let's bring up the CMakeLists in the MyCobot MoveIt config folder. And let's just go ahead and let's just copy all that. Okay, let's go over here and let's copy and paste into here. All right. Looking good, looking good, looking good. Got all of our required packages. And let's close. Now it's time to build the package. Let's open up new terminal window and use our build command. Everything is built. Okay, in a second, we're going to launch the demo and configure the plugin. So we're going to begin by going to the CD source, CD mycobot ROS2, CD mycobot bring up, scripts. Okay, and let's do sudo change mod +x, and then mycobot 280, and MoveIt. Type the password. Okay, and let's go to just do an LSLLA just to make sure everything looks good. It does. Got the permissions, which you can see over here. And let's clear. Okay, I want to make one other minor change before we launch everything. Let's open up that Gazebo and MoveIt again. And let's just set this to 0.03. I notice when this line 23, this Z value, we want the robot to be at 0.03 meters above the ground plane. And the reason for that is when I set it at 0.05, it was floating a bit. So I'm setting it at 0.03. And what about our other one? Let's see, do we need to do the same? Oops. Let's do get it, mycobot 280 gazebo.sh. And we got a 0.05 there. I'm also going to set that to 0.03. Just save. All right, folks. Now, for the time you've been waiting for. All right, let's just do another quick build. The moment you've been waiting for, it's time to launch your robotic arm. So let's do that now. I'm going to type a long command, so just bear with me here. We're going to do bash. Actually, let's do it in here. Let's do it in here, okay? Got the script in here. So let's do bash, and let's do mycobot gazebo and MoveIt. Okay, so bash mycobot _280 _gazebo _and _MoveIt.sh and run. And let this come up, and this will start Gazebo, spawn the robot, start the robot state publisher, and load and start the necessary controllers, including the joint state broadcaster, the arm controller, and the gripper action controller. This script will then start the move group node, launch RViz and the MoveIt configuration, and use the simulation time from Gazebo. So here is what your screen should look like. Everything is loaded. Here we go. I've got Gazebo on the left, and I've got RViz on the right. Looking good. Okay. Let's check the active topics. I'm going to go to a new terminal, and let's do ROS2 topic lists. And here we go. All of our topics. Let's check the active nodes, ROS2 node list. Here are active nodes. It's clear. Let's check the available action servers. We'll do ROS2 action list. Got the ARM controller, follow joint trajectory, gripper action controller. All of these. Now let's check our services. You'll see we've got a lot of services, so I'm going to ROS2 service list. Lots of different services. It is full. Lots and lots and lots. Let's check out the parameters for different nodes by launching a GUI called RQT reconfigure. So let's clear. And let's do RQT space hyphen standalone and RQT _ reconfigure. Enter. There we go. Let's expand it out a little bit. Let's click refresh. So we got everything in here. Let's expand the refresh button, that button right there. And click on any of the nodes to see the parameters for that node. For example, let's have a look at the MoveIt Simple Controller Manager node. You can see all the different parameters for that. So this tool enables you to see if the parameters you set in the config file of your MoveIt package were set correctly. All right, you can close the window. Okay, now let's run through RViz. Going to put this front and center. Let's put our robot straight right there. We can close this right there. I don't need it. Okay, let's take a look. Make it bigger so you can see. So you've got the displays panel up here. Okay, and then let's make this bigger so we can see. Okay. And I'm going to expand global options and make sure that your fixed frame is the base link. Scroll down to the motion planning plugin. Make sure the robot description field right there is set to robot description. So it should look like that right there. Make sure the planning scene topic field is set to the monitored planning scene. Let's expand the plan path. Make sure the trajectory topic under this plan path is set to display plan path. In the planning request section right here, make sure the planning group right here is set to the arm. Right there. You can also see arm is set in the motion planning panel in the bottom left as well. That's what we want. RViz has 4 different visualizations for MoveIt. These visualizations are overlapping. So let's go and take a look at the first one where we go to planning scene right here and you go down to scene robot and let's check the show robot visual. Okay. You've got the plan path for the robot, which you get from the motion planning. Plan path, where is it? Where are you? Plan path right there. And the show robot visual checkbox. Okay. That'll enable you to show the plan path for the robot if you want to. And let's go down to the motion planning request, motion planning right there, planning request, and query start state. If you check this right here, what you are showing is in green, it's going to show the start state for motion planning. And you go to the query goal state, you check that. It's going to show the goal state, desired goal state. So let's uncheck that. Okay, uncheck goal state and let's check the start state. That's in green, that's the starting point. And this is our goal right here in orange. Okay. So there we go. Let's just do the goal state right there in orange. So you can toggle each of these visualizations on and off using the checkboxes in this display panel to show different ways to visualize your robotic arm using this MoveIt plugin. Now let's interact with the robotic arm a little bit. Let's configure everything in RViz just to make sure we have everything as we want it. I'm going to go up here to motion planning and go down to plan path and make sure the show robot visual checkbox right here is checked. Okay, where's planning scene? Planning scene on the left. Okay, planning scene, we've got scene robot. And we've got show robot visual. Let's uncheck that. All right, and let's go down to motion planning, planning request, and make sure that the start state is unchecked, the query start state, and make sure the query goal state is checked. Okay. Now go find the joints tab in the motion planning panel in the bottom left. This lets you control the individual joints of the robot and try moving the sliders of the joints and watch how the robot arm changes its pose. See that? Let's move it up and down. You can see the goal state right there. Now let's go and uncheck the goal state and check the query start state in green. And so this green colored robot is used to set the start state for motion planning of your robot. Now it's time to plan a movement for your robotic arm using RViz and MoveIt 2. In the displays panel in RViz, do the following. So I want you to uncheck the goal state right there and check the start state. All right. And you can see if any links are in collision by going to the motion planning window down here at the bottom and then moving to the status tab. Let's go over here to the status tab. And we see we're pretty good. Now go back to joints over here and move the green start state to where you want the robot movement to begin. Let's just make it back. Let's start it backwards like this, 30 degrees like that. Okay, start state. Now uncheck the start state. Click the goal state. Got the goal state with the robotic arm. Okay, a little bit forward, down like that. Now I want you to check the start state and the goal state so you can see both. Here's our start state in green and our goal state in orange. Okay, to make this easier, let's go back. Let's go click the start state right here and let's just zero it out. I think that's going to be better. Start it out where it already is and then confuse everything. Change this to 0. Okay, everything's at 0. All right, so there's our start state and let's do the goal state. So start state where it is right now and the goal state down here. Let's make it simpler. Now go to the context tab in the bottom left. Ooh. Okay. Let's go see what's going on here in the status. I see something jumping around. No, it's okay. All right. Let's go back to context. And let's say I like OMPL. Okay, like that. Now click on the planning tab. Click the plan button. See that? So the plan button generates a motion plan between the start and the goal state. See that? Plan. See the robot move. And the system calculates a path, and you should see a preview of the plan motion in the 3D visualization window. Review the plan path carefully to ensure it's appropriate and collision-free. And if you're not satisfied with the plan, you can adjust the start and goal states in the 3D view and plan again. Once you're happy with the plan, you will click the Plan and Execute button, okay, to make the robot carry out the plan motion. And there we go. You should see your simulated robotic arm has moved in Gazebo. Let's confirm it. It is moved in Gazebo and in RViz. Now, if you want to speed things up, okay, you can tweak the velocity scaling figure right here on the planning tab. You know, you can tweak this right there. You can make it higher or lower, whatever you want to do. And you can keep setting different goal states by going to joint. Let's bring it back up here. Let's do another new goal state. Okay, and let's go back to the planning tab. Plan and execute. And there we go. So you just keep setting different goal states, plan and execute. And be careful not to move your robot into a goal state where the robot appears red. Okay. And some weird configuration. Let's see if I can show you what that looks like. Probably can't. Let's see. Go here. Yeah, it's pretty hard to get it into a configuration the way I've got it set up. Let's see. There we go. Okay. So you see I've clicked. So my values here for my joints. So I've made minus 72, minus 116, 156, minus 16, minus 75, and minus 72. Okay. So I just set in very extreme value for that link 3 to link 4. And you can see here we've got a collision. So you want to be careful that when you set a goal, you don't want it to be red, because that means that the robot will self-collide. Okay, let's go back up to here. And let's just plan and execute. Okay, there we are. Everything good. And by the way, if you want to open and close the gripper, the steps are pretty much the same. You're going to go to the motion planning window right there, in the bottom left. Go to the planning tab. Okay, and we are going to change the planning group to gripper. Now our planning group is gripper. And select closed as the goal state. Closed as the goal state. Move it over here. And let's do plan and execute. You can see the gripper closed. And let's just confirm that over in here. Yep, gripper is closed in Gazebo. So we've got a lot of different options here. In RViz, you can also make motion plans for the combined arm and gripper group. You can have fun with it and play around to get a feel for, this is arm and gripper group, to get a feel for how MoveIt 2 works in RViz. And you can try other planners as well. So we can go over here to the context tab. We've got other planners like STOMP and Pilz, which we talked about earlier. So I've set up Pilz and STOMP as some alternative motion planning libraries, and you just use the drop down and you can select Pilz, for example, and select which one you want, linear, and then you can plan different movements like that. Understanding how your robot moves in detail is important for ensuring smooth and safe operations. Let's explore a tool that allows us to do just that. So click on the Panels menu in the upper left. Choose Trajectory, Trajectory Slider. You can see that right here. You'll see a new slider appear in RViz. Now to plan a movement, set a new goal pose for the robotic arm. So I'm going to move this back to OMPL. Let's go to Joints. Okay, and actually, let's go to Context, OMPL. Let's go to Planning. I'm going to change it back to the arm group. And let's set a new goal state. Let's go to Joints. Let's drag this. Okay, I'm going to set a new goal. Let's get rid of that start state. That's confusing me. So here's where the robot is, and here's where we want it to go. Now we go back over here, planning, and click the plan button. Okay, you can see it moved. I have the plan button. Now we can move the slider here to see the different motions. You see that? You can move this slider here to show the trajectory from the starting location to the goal location, the different waypoints. Going from the starting location to the goal location. Starting location to the goal location. So by clicking play, it'll run through all the waypoints like that. Just clicking play. So you can see the whole trajectory. Watch the whole movement smoothly. Remember, if you change where you want the robot to go, always click plan again before using the slider or play button. This makes sure you're looking at the newest plan and not the old one. This tool is very helpful, helps you understand exactly how your robot will move from start to finish. Now, sometimes you want your robot to move in a straight line, and here's how to do that. Go to the motion planning panel on the bottom left of the screen and click on the planning tab and use the, let's see, we're going to click the use Cartesian path checkbox. Okay, and what does this do? So when you check this use Cartesian path checkbox, the robot will try to move its end effector in a straight line. This is very useful for tasks that need precise, direct movements like drawing a straight line or moving directly towards an object. Why is this important? Well, normal planning might move the robot's arm in a curved or complex path. Cartesian planning ensures a more predictable straight line movement. Try planning some movements with this option on and off to see the difference in how the robot moves. You will need to try different joint goal locations to get a plan that works, because many will fail. That's it for this tutorial. I am glad you have followed along with me from the beginning to the end. You are now fully set up, configured your MyCobot 280 in simulation for MoveIt 2 with Gazebo and RViz. Thank you for watching, and keep building.